Hello students, welcome to BTech first year bridge course. In the last lecture, we have discussed the electrostatic Gauss's law in quantitative manner. And we have seen two forms of Gauss's law. One is integral form and another is differential form. Now the differential form is new to you and the form is divergence of electric field is equal to rho by epsilon naught. Now rho is the volume charge density. Now today we will discuss this divergence of electric field when the electric field of the Coulomb types of field means if we have a point charge at the center, then the electric field is radially outward and the form of the electric field at a particular distance, suppose r, the form will be like this, right? So here this electric field is dependent on r only, right? There is no theta and phi dependency. So you know that in spherical coordinate there is r, theta and phi coordinate, right? So this electric field is dependent on r, so that means it has spherical symmetry. So whenever a parameter which is only dependent on r, that means it has spherical symmetry. Now let's apply the divergence on this electric field. Now when we consider the divergence form, so this is a operator and in Cartesian coordinate the form is I del del x plus j del del y plus k del del z. Now you know you can go from the Cartesian coordinate to spherical coordinate by three transformation equations, right? Now if we apply the transformation equations, then we will get form of the divergence in spherical coordinate. So this is the first term of the divergence in spherical coordinate. Now here we are not considering the theta and phi terms. Why? Because the electric field is dependent on r. It is not dependent on theta and phi. If it depends on theta and phi, then we have to consider the other terms. So here we are not going into those details. What will be the forms when there is theta and phi? Rather, you can see if there is a spherical symmetry, the life becomes easy, and the form of the divergence is like this. Okay, so 1 by r square del del r square. So this is the form of the divergence when we have spherical symmetry in the system. Now here this is the rth component of electric field and the rth component is 1 by 4 by epsilon naught q by r square, right? So here r square will cancel and 1 by 4 by epsilon naught, as this is constant, it will come out from this differentiation term from this parenthesis and we are left with only q. So if we operate del r on q, it will give us 0 because q is constant, right? So any derivative, if you operate any derivative on any constant, it will give you 0, right? And there is 1 by 4 by epsilon naught 1 by r square. So that's why we are getting 0. Now if we find out the flux through a Gaussian surface, means suppose we want to find out the electric field here, so in that case we have to form a Gaussian surface enclosing that point, right? So in that case total flux will be q by epsilon naught, because here as this is spherical surface, the total surface area of that sphere will be 4 pi r square and we will get q by epsilon naught. However, if we calculate the total volume integration, that will be 0 because the divergence of electric field is already 0. The integrand is already 0. So but already you are saying that the closed surface integration is not 0. So this we can tell this is a paradox. So where is the problem? So the problem is actually at the center where the charge is situated. So if you consider r equal to 0 point where the charge is situated, this electric field will blow up. This will be a large value, infinitely large value. Okay, so the correct conclusion we can draw like this, that the divergence of electric field will be 0 when r not equal to 0, but at r equal to 0, when we are operating this divergence, Actually, when this operates on this 1 by r square, divergence when it operates on 1 by r square, it will give us one term that is called delta cube r. So this will, see it very carefully that if we operate this divergence on this 1 by r square, it will give us 4 pi delta cube r, and here is 4 pi, below is also 4 pi, that was already there, so 4 pi will cancel. Okay, so divergence 1 by r square will be 4 pi delta cube r. So this delta cube is actually delta x, delta y, delta z. Now what is this actually? It is called the Dirac delta function. It is called Dirac delta function. Now Dirac delta function means, suppose if we consider only one dimension along x, so the charge is at the center. So there the charge density is very high, right? But the charge density will be very low if you go further away from this center. That's why we can tell delta x is 0 when x is not equal to 0, and delta x is infinite when x is 0. And if we integrate over minus infinity to infinity, we will get 1, that is the area of this distribution. So we can tell this Dirac delta function as a distribution function. Now here this q delta x, delta cube, delta z is basically q delta cube r, and that is actually the volume charge density. Okay, now here we are putting the volume charge density, and we will get the divergence of electric field equal to rho by epsilon naught. Now if we consider the total volume, means that is considering this point where the charge is situated, also where the divergence of electric field will be 0, that means r not equal to 0. So in that case, this will be the total divergence form. Now if you integrate, so let's go back. If you integrate over total volume, then we will get this q by epsilon naught, because rho dv, volume integration rho dv is q, and the Gauss's divergence here, Gauss's law is verified here. So this is a important point you have to remember when you are dealing with a function which is dependent on r, and it is specially 1 by r types or 1 by r square types. If you are operating this del operator, divergence or gradient, in that case you have to consider this Dirac delta function to solve this type of problem. Okay, so you have to remember this. Now today I am ending here. In the next class we will discuss the electric potential. Okay, thank you.